and welcome back to the sixth part of the first week. Last time we set up the stable matching problem where, if you recall, we had two groups of n agents each, whom we called the men and the woman, and all the men had a ranking over the woman and all the women also had a ranking over the men. And in this setup we wanted to find a matching which was 1-to-1 and which did not have any blocking pairs. What was a blocking pair? Well, it was a pair of agents who prefer each other over their matched partners. So it only makes sense to talk about blocking pairs in the context of a matching. So given a matching, you can check if there is a pair of agents that's blocking it. And if there is indeed a blocking pair, then that's not a nice matching. And what we're looking for is a matching that is completely stable, which is to say that there are no blocking pairs at all. So that was the setup from last time. And we did try to come up with an algorithm which can produce a stable matching. And we said the way it's going to work is that we start with some matching. And if that happens to be a lucky choice, it's already stable, then there's nothing to be done. But if it's not stable, then there must be a blocking pair somewhere. So let's find a blocking pair. And let's look at the agents who are participating in the blocking pair and let's match them to each other. And that will leave two other agents hanging, and let's match them as well and try to reduce the number of blocking pairs in each step. And we saw last time that unfortunately this idea, although it feels natural, doesn't actually work. And we saw an example of how this algorithm could go on forever, and that of course would be unfortunate. So in this video, we are going to talk about how we can fix this. We're not going to actually go back and modify the algorithm that we started off with, but we are actually going to look at a slightly different approach for finding stable matchings. Like I said last time, the hint is to think in greedy terms. Now, everybody is trying to get matched with their best possible partner. So our algorithm is going to leverage the spirit of this idea. So what we are going to say is that the men will propose to the woman according to their rank lists. So to begin with, for example, all the men are going to propose to the woman who is on the top of their rank list. And as far as women are concerned, they are also going to be looking at this from a greedy perspective. So they are going to accept the best offer that they have. If they have just one offer, then they're going to accept it, because we're going to assume that being matched is better than being unmatched. But on the other hand, if you happen to be spoiled for choice and that you have multiple proposals to consider, then you pick the best one from your point of view. So remember that the women also have a ranking of the men, and if they receive multiple proposals from some subset of men, then they're going to pick the one that comes from the highest ranked man in that subset to engage with. Now, if a man M makes a proposal to a woman W and she happens to accept it, then this pair MW is said to be engaged to each other. And you might notice that the term engage has a temporary ring to it, as opposed to saying that M is married to W or something like that. And that's actually intuitive, because it's in the nature of the algorithm that these associations are in fact temporary, as we will see as we go along. But for now, we've talked about what happens to begin with. All the men bravely propose to the woman that they rank at the very top. And what happens as a result of this is that some women receive a proposal, some receive multiple, and perhaps some receive none. For the women who don't receive any proposals at all, they have nothing to do. For those who receive exactly one proposal, they immediately engage with that one proposal that they get. And for those who receive multiple offers, simply engage with the best of them. So that's what happens to begin with. What happens in general? Well, in general, we are going to always be in a situation where we have some engagements and we have some people who are not yet engaged. So let's focus on the men who are not yet engaged. It'll be convenient to refer to such men as the set of single men. So as long as we still have single men, what we are going to do is have them propose to their best option among those who they have not yet approached. So what that means is that from the perspective of a man, perhaps they have proposed to a woman already and they have been rejected, presumably because the woman in question had a better offer to consider. So when a man is rejected in this algorithm, what they do is they just move on to the next element in the ranking and they propose to their next best option, and this continues. From a woman's perspective, when they receive an offer or they receive multiple offers, now there can be two situations in general. To begin with, a woman, in fact all the women, were single. Now, at a general stage of the algorithm, it's possible that a woman is already engaged to somebody, and in this situation, we have to think carefully about what happens when she gets a new offer or potentially multiple new offers. Remember that for women who are not engaged, if they get offers, that's easy to deal with because, like we said, it's better to be matched than to be unmatched from the perspective of this algorithm, because at the end of the day, we do want a perfect one-to-one matching. We want to make sure that everybody is matched. So it's intuitive that if a woman is not yet matched and they receive an offer or multiple offers, then they actually go ahead and engage. The more interesting question is perhaps the situation of women who are already engaged to some man. So let's say W is already engaged to M and she receives an offer from another man, M prime, who was perhaps single, and W happened to be the next best preference in his list. Now, if it turns out that W prefers M prime less than M, then it's perhaps reasonably clear that W would not want to break off this engagement in favor of a man she prefers less. But what if W prefers M prime more than M? In this case, should she break off the engagement and take up M prime's proposal, or should she stick to what she already has? Think about that for a second. Think about what would be the right move here from the perspective of the algorithm, which is trying to get to a stable matching. Think about it from that point of view. Feel free to pause and go back and recall what blocking pairs are, because that's what we are trying to avoid. So that's a hint here for how you might want to approach this question. All right, so I hope you took that pause and you had a chance to think about this. Let me just quickly recap the scenarios from the woman's perspective overall. So at any general point in the algorithm, once the men who are currently single have proposed to the women who are on the top of their current preference lists, which is to say after ignoring all the women they have been rejected by so far. And now once these proposals have been made, from the perspective of the woman, we have three scenarios. The first is women who receive no proposals, well, no action to be taken because there's nothing to do. Now, for women who receive multiple proposals, and that's one proposal or more than one proposal, well, what they want to do is really work with the best proposal that they have, and that's based on their ranking of the men. But the real question is, if the best proposal that they have is coming in a situation when they're already engaged to somebody, then is it worth breaking the engagement off to take up the better proposal? So we want to argue that indeed the women are better off breaking their current engagements to take up the new proposals if they are better. And let's think about why. The reason for this is the following. Suppose WI is currently engaged to MJ at some stage of the algorithm. So WI is the woman, MJ is the man. And let's say MK, who is another man who is currently single, comes along with a proposal for WI. And let's say also that in WI's mind, MK is the better choice compared to MJ. So this new proposal is superior to her current engaged partner. Now, what do you think will happen if this proposal from MK is rejected at this stage of the algorithm? If that happens, then in the final matching that you output, we are going to have a situation where MK and WI will end up forming a blocking pair. Let's think about why this is going to be the case. Because this proposal was rejected and the way the algorithm works, the men are only going to propose to women who have not yet rejected them. So once MK has been rejected by WI, he's not going to come back and propose to her again in the algorithm, which means that in the final output, the man MK will be matched to somebody other than WI, and whoever that woman is going to be somebody that MK ranks lower than WI. Why is that? Because remember that the men only move further down their rank lists and they never come back up. So once this rejection has played out, MK is definitely going to get matched to somebody who is worse than WI from his perspective. What about WI? Well, we already know that WI prefers MK over MJ, and if she has adopted a policy of rejecting proposals throughout just because she is currently engaged to MJ, then she's going to remain engaged to MJ till the very end. So we have a situation where WI will prefer MK over MJ and MK will prefer WI over whoever he is matched with. And so that's a recipe for a blocking pair, and we want to avoid this situation. We don't want to be here at the end of the algorithm. So in the interest of longer term stability and happiness, we will have to make a difficult decision here to actually break off this engagement, because that's the sensible thing to do, anticipating our need for not having any blocking pairs at the end. Okay, so that's the entirety of the algorithm. You can also cross-check the course notes for a pseudocode version of it, which shows you step by step what's going on. And there are also pointers to notes where there are a lot of implementation details. This is a fun algorithm to try and implement yourself. But I do hope that the overall mechanics of what's going on is reasonably clear. Let me just quickly recap it so that we are on the same page, and then we will try it out on this example just to reinforce our understanding of what is going on. All right. So to begin with, we have n men and n women. In this example, n is 3. And at the beginning, all the men and women have a status of being single. Now the algorithm proceeds in rounds, and at any round what we do is we ask all the men who are currently single to propose to the woman that they rank the highest, but only among those women who have not rejected them so far. So every man individually keeps track of all the women that they have proposed to so far, and they may have been engaged, engagements may have been broken off, and so on. And as the algorithm progresses, the men move further down their preference list. So that's what's happening from their perspective. So at the start of any given round, we are going to ask all the men who are single to propose to their best option currently, not counting those with whom they have already made a proposal and been rejected. So that's what the men do at the start of the round. From the perspective of the woman, well, we have two scenarios. One is that a woman doesn't receive any proposals, in which case there's nothing for her to do in this round. On the other hand, it's possible that a woman receives one or more proposals. The simplest situation is when a woman is single and she receives one proposal. In this case, she just accepts it. But it could also be that a woman is single and she receives multiple proposals. In this case, she engages with the best proposal from her perspective. Finally, you could be in a situation where you have a current engagement with some man and you receive one or more proposals. In this case, you evaluate the incoming proposals, and if the best among them is better than your current engaged partner, then you break off the engagement and pick up a new engagement with this new proposal, right? And if all the proposals you receive are worse or lower ranked than the man that you're currently engaged with, then there is no change, and all these men who have made the proposal go back to being single. And now these rounds are going to repeat for as long as there are single men in the pool. Now, of course, in the last video, we did see an example of an algorithm that wouldn't terminate in general. We saw an example of an input on which it would go on forever. So I would understand if you're concerned about whether the algorithm that we just described might also suffer from the same problem, because our outer loop is effectively going to be something to the effect of, while there exist single men, we are going to have them make these proposals. However, notice that in the current algorithm, what's happening is that a man never makes more than n proposals because they never propose again to a woman who has rejected them. Therefore, the total number of proposals that can happen in any run of this algorithm is at most n squared. So that's an automatic termination condition, because if nothing else, what will happen is that the men will run out of people to propose to. And what's really nice about this is that by the time that happens, you're also guaranteed to actually have a perfect one-to-one matching. And we'll talk about this in a little more detail in the next and the final video. But for now, let's just do a walkthrough of this algorithm on this example that you have been looking at for some time on your screen. So here we have 3 men and 3 women, and the preferences are as given. And let's go ahead and see what happens when we run this algorithm on this example. So first we have the men on the right hand side, A, B and C, proposing to their favorite woman. So A and B are going to propose to Q, and C is going to propose to S. So from the point of view of the woman now, what's happened is that Q has received 2 proposals, one from A and the other from B, and R has received 0 proposals, and S has received 1, which is from C. So what are the engagements at the end of this round? Well, it's pretty clear that C is going to engage with S because S does not have any other options, and R is going to remain single because she has received 0 proposals. And here Q is the one who is spoiled for choice. She has 2 proposals, and between A and B, she prefers B more than A. Notice that B is not her top preference, but it's still the better preference between these 2 options. So we are going to have B engage with Q and C engage with S at the end of this round. So those are our 2 engagements, which you can see highlighted here. And now we are going to have the men progress further down their preference lists, and we are going to have the next proposal come from A, because currently A is the only single man in the instance. Everybody else has an engaged partner. Who is A going to propose to though? Well, A is going to propose to their top preference among the women who have not yet rejected him. So notice that Q has already rejected A, and that's why we have removed Q from A's preference list, because that's not someone he's going to ever come back to. And so at this stage, A proposes to the next best option, which is S. And what's the situation with S? Well, the scene is that S is already engaged with C, but C is actually, from the perspective of S, their worst possible partner. So when S does receive this proposal from A, they are going to break off their current engagement and actually take up the offer from A. So this is what the current situation looks like. So we still have R being single among the women because she didn't get a proposal in the second round either. But as far as the men are concerned, the situation has changed a little bit. B remains engaged to Q, but A went from being single to being engaged, and C went from being engaged to being single. Had A been rejected in the second round as well, then the situation would have been the opposite, where A would have continued to be single and C would have continued to be engaged, as would have been B. But this is the situation we have right now, and so the only single man is C, and we are going to have him propose to the current best option, which as you can see is R. And we know that R is single, and when a woman who is single receives a proposal, she simply accepts it. So we are going to add R and C to the list of engaged partners. But at this point, notice that nobody is single, and we've managed to match everyone, and we have a one-to-one matching. Now I'll leave it as an exercise for you to validate that this matching indeed has no blocking pairs. And this is no coincidence, it's actually a property of the algorithm that it always outputs a perfect one-to-one matching which has 0 blocking pairs. This should not come across as surprising because the whole circus that we did with the woman rejecting the men whom they're even engaged to in favor of better proposals was designed to avert blocking pairs. And we will see how those choices actually play into the proof of correctness of this algorithm. So that's going to be the last thing that we discuss this week. So in the final video, we will come back and prove that this algorithm always terminates in a perfect matching, which is actually completely stable. So that's a really cool result, and I'm looking forward to discussing it with you. Thanks, and see you next time.